Hello and welcome to another Common Core Algebra 1 lesson by eMathInstruction. My name is Kirk Weiler, and today we're going to be doing Unit 4, Lesson number 7, More Linear Modeling. Before we get started on this, let me remind you that the worksheet and a homework for this video can be found by clicking on the video's description or by visiting our webpage at www.eMathInstruction.com. As well, don't forget about the QR codes at the top of every sheet. Scan those with your smartphone or your tablet to bring you right to this video. Alright, let's begin. Now, we've already spent an entire lesson on doing linear modeling, i.e. taking real-world scenarios where two variables are related by linear functions and writing equations, predicting outcomes, checking those outcomes, etc. But linear modeling is one of the cornerstones of Common Core Algebra 1. It's one of the things that you should come out of this course being fluent in. Fluent, meaning that you can do it as easily as you do addition and subtraction. Okay? So we're going to spend another day on it, another lesson, and let's jump right into exercise 1. A warehouse is keeping track of its inventory of cardboard boxes. At the beginning of the month, they had a supply of 1,275 boxes left. Okay, so that's what they're starting with. And they use boxes at a rate of 75 per day. Letter A asks, how many boxes are left after 10 days? Show the calculation that leads to your answer. Pause the video now, think about this, and see if you can come up with an answer. All right, let's go through it. Well, for a lot of students, they're going to do the following. They're going to say, well, all right, I use up 75 boxes per day, right? 10 days have gone by, and that means that we've used up 750 boxes. But of course, we started with 1,275 boxes. So we subtract off the 750, and we find 525 boxes are left. Okay? So after 10 days, 525 boxes are left. Now, letter B then asks us to extend this, right? And this is actually almost the biggest thing in algebra. Can you now go from saying how many boxes are left after 10 days to how many boxes left after D days, right? So N is the number of boxes, D is the number of days. Which of these four choices gives us the number of boxes left after D days? Okay, pause the video now and see if you can figure it out. All right, let's go through it. Well, think about what we did, right? What we did is that we took 75 and we multiplied it by the number of days, right? And that's how many boxes we had used. But then we took that amount and we subtracted it from 1,275, right? And that gave us the number of boxes left, right? That's exactly what we did, right? This was 1275 minus 75 times the number of days. So the only difference between these two is in this case, I know the number of days is 10. In this case, the number of days is left as a variable. And therefore, choice 3. All right? Let's take a look at C. If the warehouse needs to order more boxes when their supply reaches 150, how many days can they wait? Pause the video now, see if you can figure this out. All right, let's go through it. Well, right now we know that this equation, if you will, models how many boxes we have left according to how many days we've been using the boxes. Now that 150 that they gave me is my N. It's the number of boxes I have left. So I'm going to put that into my equation and I'm going to let my algebra do its magic, right? I'm going to solve this equation now. I'm going to subtract 1275 from both sides. That's going to be a little bit obnoxious because it's going to leave me with a negative. But I can deal with that, right? Especially if I'm using my calculator. That'll be negative 1,125. Sorry, I'm looking over at my cheat sheet every once in a while, i.e. my answer key, equals negative 75 times D. I can now divide both sides by negative 75. And what I'll find is that D equals 15. 15 days before I get down and have to order more boxes. Now, letter D. Sometimes math can kind of switch around on you right in the middle of a problem. That's life, right? Letter D. If after 5 days, right, 5 days have gone by, they start using boxes at a rate of 90 per day, right? So we were using them at 75 per day, now 90 per day. How many days will it be before they run out of boxes? Show the work that leads to your answers. So this is kind of cool, right? Pause the video now and see if you can work through this. This is a real world problem. All right, let's go through it. Well, what we may want to do is figure out how many boxes we have left after 5 days, right? So after 5 days, 1,275 minus 75 times 5 leaves us with 900 boxes left, right? Now we start using them at 90 per day, right? So let me just set up a real quick equation. Let's do 90 times the number of days equals 900, right? 90 times the number of days equals 900. Divide both sides by 90, and we get 10 days. So it's going to take us 10 additional days before we run out of boxes, or a total of 5 plus 10, or 15 days. I know, by the way, that that's exactly the same answer we got in C, but that's a complete coincidence. Just totally different problem. And quite frankly, I probably should have designed it so it came out to be different, but it's a total of 15 days. And it's kind of neat. Really what we're dealing with in D, and we'll talk about this later on in the course, is a piecewise linear function, right? It was linear with a slope of negative 75 for the first 5 days, and then it became linear with a slope of negative 90 for the remaining, I guess, 10 days, if you will. All right? So I'm going to clear out the text, write down what you need to. All right, here it goes. Let's do some more with linear models. Exercise 2. The cost, C, in dollars, of running a particular factory that produces W widgets can be modeled using this linear function. By the way, if you don't know what a widget is an object that a company produces when a, let's say, worksheet designer is too lazy to come up with a real product. So a widget is like an imaginary product that a company produces. Okay? So anyway, the idea though here is that, now notice, right, function notation, that's all that is. Function notation. All right. Just says that the cost in dollars of running a particular factory is based on the number of widgets it produces, right? That's the number of widgets it produces. It's given by that equation. Now, letter A is just an interpretation. It says, how do you interpret the fact that C parentheses 100 equals 2300? All right. Pause the video. See if you can write down how you interpret that piece of information. Okay, let's do it. Well, here's the input, right? So that's the input, right? So that there's 100 widgets, right? And this is the output. What was the output? That was the cost. So I would interpret it as the following. It costs $2,300 to produce 100 widgets in a day at this factory. That's my interpretation. Now letter B says give a physical interpretation for the two parameters. Remember the linear parameters in this equation of 1.25 and 2,175. So what do those mean in the real world? What do those mean? All right, pause the video and see if you can write down how you interpret those two numbers. All right, let's do it. I'm going to actually start with the 2175 first, okay? All right, 2175 represents the cost to run the factory even when 0 widgets are produced. So very often, a company, even if it doesn't make any product in a given day, a bicycle company, a car factory, whatever, it still has costs, all right? These things are what are known as fixed costs in economics. Fixed costs, all right? And it makes sense, right? You got to heat the place, there's the rent, there's taxes, right? There's all sorts of things. So even if you don't build a single widget, it still costs money to run this factory. Now, what does the 125 represent? Well, this one's a little bit trickier, but remember, this is a slope, right? So it's the change in C divided by the change in W. We write it as this, 1.25 divided by 1. So what this represents, the 125 represents that each additional widget will raise the cost by $1.25. All right? So each widget that's created, right, an increase in one widget represents an increase in cost of $1.25. Okay? And slope always has an interpretation like that. As this thing goes up by 1, this thing goes up by whatever. All right? So, pause the video now, write down whatever you need to. Okay, let's clear it out. Keep on modeling. Let's talk about deer. In the Northeast, we have a lot of deer. I don't know where you're living, but I see them all the time. And unfortunately, my car sees them sometimes. Biologists estimate that the number of deer in Rhode Island in 2003 was 1,028. Rhode Island's a tiny state. No offense if you're in Rhode Island. And in 2008, it had grown to 1,488. Biologists would like to model the deer population P as a function of the years T since 2000. Okay, so in other words, this is my output, and this is my input. Okay? First thing we're asked to do is represent the information that we've been told as 2 coordinate points. Be careful to know what your values of time are for each year. Now, why does it say that? Well, it says that because we want T not to be the year. We don't want our input to be 2003. It's the years since 2000. So in other words, the first piece of information they give us actually occurs at year 3, right? 2003 is 3 years since the year 2000, and there are 1,028 deer. The second piece of information we're given is at year 8, and that's 1,488 deer. All right, letter B says calculate delta P divided by delta T. In other words, the average rate of change. Also known as the slope. All right, and it says include units in the answer. Why don't you go ahead and do that? You've got the 2 points in A. Calculate that average rate of change. All right, let's do it. So delta P divided by delta T, we'll take our second population, 1488, minus our first population, 1028, divide it by 8 minus 3. Okay, do a little cheat sheet here. 460, watch me track the units right now. 460 deer, right? Divided by 5 years gives me 92 deer per year. There's my average rate of change. Letter C asks us to interpret that. So how do you interpret that value? All right, let's go through it. We interpret it by saying each year the deer population increases on average by 92. That's it, right? For every 1 year, the deer go up by 92. Finally, it asks us to determine a linear relationship between the deer population and the years since 2000. Now, the nice thing is, here we're doing P equals MT plus B, right? Y equals MX plus B, except instead of Y we have P and instead of X we have T. We already know the M, so we can actually start right here. P equals 92 times T plus B. The only thing that we don't know is this, but in the last few lessons we've seen this repeatedly. In order to calculate the y-intercept, once we know the slope, we simply need to pick one of the 2 points that we have, substitute it in. I almost always take the first one because, hey, why not? But it shouldn't matter. All right, we're just going to substitute that in. We'll get 1028 is equal to, where am I at here? 276 plus b. Subtract 276 from both sides. Ooh, running out of space. Way down at the bottom. B is equal to 752. So now we have our model. P is equal to 92t plus 752. All right. So now again, this is just a model. That's all it is. We don't really know whether or not the population of deer is linear over this 5-year span of time. And we don't know what's going on outside of the 5-year span of time. But we do know that that line passes through those 2 points. So we're going to continue working with this example, or this exercise in just a minute, but I still have to clear out the screen. So pause the video now and write down anything you need to. Okay, here we go. Let's keep moving on. All right, so there's our model. P equals 92t plus 752. Just wanted to make sure we had it again. Letter E, how many deer does the model predict were in Rhode Island in the year 2000? What does this represent about the linear function? All right, well, pause the video and think about that for a moment. Okay, well remember, T represents the years since 2000. So if I want to know how many deer were there in 2000, that means T is equal to 0. Of course, I can put that into my model if I need to, right? But then again, 92 times 0 is 0. So there were 752 deer there, based on my model. And this is the y-intercept. Right, so if I were to draw a graph, it would start at a y value of 752. Letter F pretty much depends on when you're watching this video. It says, how many deer does the model predict for Rhode Island right now? So for me, right now, the year is 2014. So T is equal to 14 years. So the population of deer now, using my model, is 92 times 14 plus 752. That's going to be 1288 plus 752. And that gives me the population of deer at 2040. All right. So whether or not the linear model is good that would all depend on whether or not there's actually 2,040 deer in Rhode Island right now. So if we were a wildlife biologist and we wanted to check it, we would now do some kind of a survey. We would come up with an estimate for the number of deer that are in Rhode Island, and if it was close to 2,040, we would feel pretty good about our linear model. Okay, I'm going to clear out the text, and we're going to do one last exercise. Okay, let's do it. Here we go. Exercise number 4. Water is draining out of a bathtub such that the volume still left, G gallons, is shown as a function of the number of minutes, M, it has been draining. So letter A says calculate the average rate of change of G over the interval the interval 0 to 2, include proper units. All right, so I want to calculate the average rate of change over this interval. What I'd like you to do is pause the video right now and go ahead and do that. That shouldn't be too bad. All right, let's go through it. So it's going to be change in G divided by the change in minutes. All right. Watch out, always do the second one minus the first one. 28 minus 62 divided by 2 minus 0. That's going to be negative 34 divided by 2, or negative 17. Include proper units. That's always easy. Look at the units at the top. Those are gallons. Look at units at the bottom. Those are minutes, so negative 17 gallons per minute. All right, in other words, the volume is going down by 17 gallons for every minute that goes by. Now it says, calculate the average rate of change for 2 to 4. Include proper units. Again, pause the video and go ahead and do that. All right, let's go through it. Delta G divided by delta M is going to be 12 minus 28, all divided by 4 minus 2. That's going to give us negative 16 divided by 2, and that's negative 8, same units, gallons per minute. Now, letter C is extremely important. Why can we say that the relationship between M and G is not linear? Pause the video now and see if you can write down a good, albeit brief, explanation. All right, let's go through it. It's really this simple. Going back to blue, the relationship is not linear because the average rate of change is not constant. Right? So the whole point of a linear function, what makes a linear function linear is that the average rate of change, the slope, remains the same. It doesn't matter what 2 points you pick, we'll get the same. So if we had gotten negative 17 gallons per minute and another negative 17 gallons per minute, then we would say, look, the evidence supports that this is linear. All right? But since those two average rates of change aren't the same, this relationship cannot be linear. All right, it's a very important fact. So pause the video now if you need to, and then we're going to clear out the text and finish up. All right, here we go. So that concludes sort of a 2-lesson block on modeling with linear equations. Okay. Linear modeling, as I said, is one of the most important skills to develop in Common Core Algebra 1. It's one of the skills that we want you to be fluent with by the time you're done with the course. And of course, you'll work with it more and more in other courses, but this is where you really get the most intensive piece of it. Okay, for now, I'd like to thank you for joining me for another Common Core Algebra 1 lesson by eMathInstruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.